Okay, now this is probably the very last video in Chapter 7 and 8, the Intro to Quantum Mechanics. I left off, I was talking about trends in the periodic table, and I was talking about ionization energy, and I stumbled a little bit saying, why did I mention valence electrons? Now I'll come back to that and tell you why I mentioned that. So, I was saying that the ionization energy actually decreases slightly, it turns out, as you go down an atom. And that's mostly because as the atom gets larger, the valence electrons are further away from the nucleus. And again, I mentioned valence electrons in that when we talk about potassium here, even though it has 19 electrons, 18 of them are in completed inner shells. So from a reactivity standpoint, it turns out, potassium really only has one electron of interest. It takes an enormous amount of energy to get rid of a second electron. And you can actually look at the book actually covers second ionization energies of elements in the 1A group. And sure enough, when you look at potassium, the first ionization energy is pretty low. The second ionization energy is off the charts, which makes sense because getting rid of the outer valence electron that it has in the 4s orbital is pretty easy. But to get rid of a second electron, you'd have to tap into this filled 3p orbital that we already filled here when we got to argon. And that takes a lot more energy to release that. Generally speaking, when you're talking chemically about an element, after you complete a shell, once you get to a noble gas, the other electrons, those inner electrons, are really, they don't factor in chemically into bonding or to much else. Now, they're there, of course, and so they definitely affect some of the geometry, and they affect some other concepts that the book talks about called shielding and penetration a bit, but they're really kind of lesser effects. Okay, so back to ionization energy. The valence electrons are the only electrons that we're talking about in terms of ionization, which is why the second ionization energy of sodium is ridiculously high. Now, compare that to magnesium. Magnesium has 2 electrons in its outer shell. So basically, the 3s orbital is completely filled for magnesium. Remember that before, it's 3s filled. So getting rid of 1 electron would take it to 3s half filled, which would take it to an electron symmetry, kind of like sodium. And then to get rid of the second electron would be get rid of that other 3s electron, which isn't going to be terribly high either. But to get rid of a third from magnesium would be ridiculous again, because now we'd be tapping into the an electron from a filled inner shell. Okay, so that's all I want to say about that. Now, the last trend that I wanted to cover was electron affinity, and all electron affinity is take something like chlorine and add an electron. So electron affinity is how much of an affinity does chlorine have for an electron. This would of course turn into Cl minus. Okay, and the delta H for this reaction is generally negative, meaning to pick up an electron, generally speaking, stabilizes the element. I believe that's true. I think there's a table here that shows some of the electron affinity. Maybe I saw it somewhere, but maybe I didn't see it in this chapter. Oh, there it is. Figure 8.20 shows that for at least certainly for elements in the 7A, they have fairly high electron affinities, because picking up an electron takes it to that nice stable configuration of the nearest noble gas. And so in the same way that the 1As had a fairly low ionization energy, meaning it was easy to kick off an electron, the 7As have quite an electron affinity. They love to pick up electrons. Okay, and you can look at the charts, and it kind of shows that there are indeed some trends as you go across the periodic table. I think generally speaking, the electron affinity goes down as the atoms get bigger. I think that's generally across the board, and they certainly become more electron affinity as you go across. Okay. All right. I think that's all. Well, no. So there's one last thing I want to cover, and I think, yeah, I think I can get in here. I just want to cover just the rest of the chapter talks about metallics, and there's some interesting stuff in the metallic in that section. Like it's 8.4 or whatever that section is, 8.5 maybe. The one key thing I want to that I want to take away here has to do with the magnetic properties of elements. And if you remember when we were talking about chromium, and we were filling chromium, and again, chromium is going to have chromium has basically 1s2, meaning in the 1s orbital. By the way, I never introduced this form, but chromium has 1s2, and of course it has 2s2 and 2p6. That takes us to here, and then it has 3s2 and 3p6. That takes us to here, and then it has 4s1. Remember that was the oddball case. Had 1 and 3d5. Okay, so I want to introduce this. This is there's a word for this. It's called the standard form or standard configuration form or something like that. A lot of times this is abbreviated by essentially saying chromium is the same as argon, meaning replace all of this gobbledygook with argon, and then it's 4s1 and 3d5. Okay, so you'll see this a lot of times when we're in the text, at least when we're talking about elements and trying to look at essentially just looking at their valence electrons. And again, this is a case where all of the inner stuff is really not that interesting, so you can kind of abbreviate it like this and just focus on the valence electrons. So in the case of chromium, as I described in, I think it was in the previous video or maybe the one before that, it basically has, in the 4s, it has 1 electron, and in the 3d, it has 1 electron in each of the 5 orbitals. So it's 3d is completely half filled, and the 4s is half filled as well. Now, going back to, if you remember what when we talked about Pauli exclusion, is that the fact that you can even have 2 electrons in an orbital essentially means that one has 1 spin, like a positive spin, and then the other has the opposite spin, like a negative spin. So, and again, there's another rule, it's called the Hund's rule, I think, is that as you're filling orbitals, they all kind of go in with the same spin. So in this case, all 6 of these valence electrons for chromium all have the same electron spin. Well, this actually generates, each one of these electrons as they're spinning, generates a little mini magnetic field. And this is another subject, but a spinning electric field actually generates a magnetic field in the same way that a spinning magnetic field generates an electric field. These are all part of Maxwell's laws, and it's all quite interesting. But all I want to tell you is that in this case, we can look at this and say, I bet you chromium has magnetic properties. And of course, chromium does have magnetic properties. But you can also even look at I want to look at iron also, because iron, as we know, has magnetic properties. Go back to my table here for iron. Where are you, iron? There you go. Okay. Iron, if you look at the iron metal is the same as argon. Okay, and I'm reading from table 8.4. It has 4s2. In fact, I'm not going to draw it that way. I'm going to draw it as 4s and 3d. Look at iron. 3d is what looks like this. Okay. All right. So you could look at this and say, I bet iron is somewhat magnetic. And of course, iron is indeed somewhat magnetic. But if you look at the iron 2 plus cation, the ferrous iron basically is losing 2 electrons. I bet you can guess which 2 it's going to lose. The 2 it's going to lose are 1 from the 3D and 1 from the 4s. Kind of starts looking like chromium, doesn't it? In fact, I think it looks exactly like chromium. So iron 2 is very magnetic, and iron 3 plus, which is ferric, it loses that one. And so it's also magnetic as well. And so anyway, the chapter talks about trends in metals, and it talks about magnetic properties, and it also kind of plays around with these ions when you actually look at some of the metallic cations, what their electron structure looks like. And you can make a determination, is this magnetic or not? The last interesting one I'll cover is zinc. I've got to erase iron for a moment. We'll put in zinc. Again, zinc is way over here, so it's just like argon. S4 is filled, S3D all filled as well. So zinc metal is definitely not magnetic because all the electrons are paired. There aren't these little micromagnetic fields being generated. And in fact, even zinc 2 plus, which is the common cation of zinc, zinc 2 plus gets rid of these two. I shouldn't do that, leave that here. And zinc 2 plus looks like this. Okay. So nice and stable here, loses these two, still not very magnetic. Okay. So there's a number of other stories, other elements that they talk about in this, but these are kind of the main themes I want to cover in the video. Okay, I believe that takes us to the end of chapter 8. And again, this is now, with this, and in fact, all of this discussion of orbitals, the rest of the course is now just going to assume that we understand s orbitals and p orbitals, and we'll be talking about them a lot, especially the s's and the p's, as we talk about the remaining subjects, which is about bonding, molecular shapes, and some of the theories behind bonding. Okay, and that'll be coming in the chapters 9, 10, and 11.